Hello, my name is Marco Huber from Fraunhofer Institute for Computer Graphics Research, IGD, in Darmstadt, Germany, and I will present on behalf of my colleagues Antti Lu, Fadi Botros, Arjen Kuiper, and Nazer Dame our work Bias and Diversity in Synthetic-Based Face Recognition. Synthetic data is imagined as a substitute for authentic data to solve ethical and legal challenges in handling authentic face data in some jurisdictions such as the European Union. Additionally, several large face datasets such as the widely used MS-SLAB 1 million or VGG Phase 2 are not available anymore from an official source due to different reasons. However, the existing accuracy gap between authentic and synthetic-based face recognition models requires novel solutions to train suitable, well-performing face recognition models on synthetic data. It is also a known and sensitive problem that face recognition systems are susceptible to bias, so performance differences between different demographic or non-demographic attributes, which can lead to unfair decisions. In this work, we investigate the bias and diversity in synthetic-based face recognition. To do this, we investigate the distribution of head pose, gender, ethnicity, and age in 3 recently published synthetic face datasets, as well as on the authentic face datasets that were used to train the synthetic data generators, using different attribute predictors. We also investigate the bias of synthetic-based face recognition models regarding gender, age, ethnicity, and head pose in comparison to a baseline model which was trained on authentic data. To investigate the diversity of the datasets, we use different high-performing attribute predictors to predict the 3 demographic attributes, gender, age, and ethnicity, and the non-demographic attribute head pose. We then report the different distributions of the attributes of the different authentic and synthetic datasets. The investigation of the diversity of the authentic datasets is also of special interest, as investigated datasets are used to train the generative models that then create the synthetic datasets. Investigating this allows possible insights into how the distribution changes based on the utilized training data. Since investigated datasets do not provide human-labeled attributes and labeling large datasets is expensive, and there's also no factual self-reported ground truths in synthetic data regarding specific attributes because persons do not exist in real life, we utilize attribute predictors to get automatic attribute labels. The gender predictor we use is based on the VGG16 architecture and was pre-trained on ImageNet and fine-tuned on the IMDb wiki dataset. For the age predictor, we utilize a support vector machine trained on feature embeddings extracted using elastic phase and trained SVM on the audience dataset. For the ethnicity predictor, we also used the SVM, but trained it on the elastic phase embeddings of the balance phase dataset. For that post predictor, we use the pre-trained estimator named HopeNet. For all the predictors, we report the accuracies on the test benchmarks in the paper. Since in some cases different samples of the same identity might have conflicting attribute predictions, we also want to gain insights into the intra-identity distribution of the attributes. Differences in these attributes might be natural, for example due to aging processes or movement with the head, or due to less distinct features. We propose a novel intra-identity attribute consistency ratio, IACR, that provides insights into the consistency of an attribute within the images of an identity. It is a mean of the consistency of an attribute in an identity in the dataset. For some attributes such as gender or ethnicity, this value is expected to be 1, as individuals rarely change their gender or ethnicity. In synthetically generated face images, where the creators rather aim at preserving or creating the synthetic identity, than maintaining the similar attribute for the different samples, we assume that these attributes or this consistency might vary more often. For other attributes, such as head pose and age, we assume that a lower value might be favorable, as this indicates that these datasets show more natural variety in the face data. To investigate the bias in face recognition models trained on synthetic or authentic data, we analyze performance differences depending on the investigated demographic attributes. To obtain these performance differences, we evaluate different datasets that make a distinction regarding the specific attributes. For the evaluation in terms of gender bias, we evaluate on the balance phase in the Y dataset, which provides gender-based subsets. For the evaluation of the ethnicity bias, we also utilize the balanced face in the white dataset, but also the racial face in the white dataset. Both provide also ethnicity-based subsets. The age bias is evaluated using LFW and comparing the performances across age LFW dataset. For the pose bias, we utilize the CFP images and protocol and compare there the frontal-to-frontal setup with the frontal-to-profile setup. We then report the verification accuracy, but also the mean accuracy and standard deviation over the different attribute subsets, and also the skewed error ratio as proposed by Wang and Deng. To investigate the bias in face recognition models trained on synthetic data, we utilize 3 different recently proposed models trained on their associated synthetic training dataset. The utilized models are S-face, SynFace, and U-SynFace. We choose these models because they provide state-of-the-art synthetic face recognition and are also of different nature in their approach. All models used are publicly available and have been released by the authors of the respective works. As a baseline, or as an authentic baseline, we use a face recognition model trained on Casio web face with cross-face laws that also utilize the ResNet 50 architecture. This model is considered in our evaluation as a similar approach was done by some of the synthetic face recognition model to use this model as an authentic baseline. In the diversity analysis, we analyzed 2 authentic datasets, Casio web face and FFHQ dataset, and this model has been used during the generator training, and we also investigate 3 different synthetic datasets, S-face 60, Syn 10K50, and the U-Syn face 400K dataset that has been created by the generators. U-Syn face and Syn 10K50 have been created by Disco FaceGAN, trained on the FFHQ dataset, while S-face 60 has been created using StyleGAN, conditionally trained on the Casio web face dataset. The distribution of the gender attribute is visualized in the figure on the left. The dotted line indicates an equal distribution. While the FFHQ dataset, U-Syn face 400K dataset, and the Syn 10K50 dataset are nearly balanced, the imbalance of the gender distribution in the S-face 60 dataset increased in contrast to its generator training data, Casio web face, which might indicate that the generative model tends to create samples from its majority class regarding the gender distribution. The ethnicity distribution is shown in the figure on the right, and the figure shows that there is a high imbalance distribution in the authentic but also in the synthetic face datasets. White Caucasian individuals are highly overrepresented, while other ethnicities are underrepresented. One can also note that the synthetic dataset follow, to some degree, the overall distribution of the respective generated training data. For example, the authentic FFHQ dataset contains more Asian identities, which lead also to more generated Asian samples in U-Syn face 400K, in contrast, for example, to S-face 60. The numerical values of all the distributions are also provided in the paper. Similar observations can be made for the age distribution. Again, a high imbalance can be seen across the datasets, and some classes, such as children or seniors, which are underrepresented in the authentic datasets, are also underrepresented in the synthetic datasets. The general distribution of the attributes remains the same in the respective generator training dataset. Similar is also true for the head pose distribution. This table shows the IAACR values for the authentic Casio web face dataset and the 3 synthetic dataset. It can be seen that S-face 60 and U-Syn face dataset show a similar IAACR as the authentic Casio web face dataset, indicating that the most images of the synthetic individuals share the same attribute features. The Syn 10K dataset shows less consistency, which might be due to the identity mixup performed to create the synthetic images. Regarding the bias, it can be seen that all models, including the authentic model, perform better on male faces than female faces. While the standard deviation indicates less bias in the authentic model, the skewed error ratio indicates higher bias in the authentic data. The authentic-based baseline model, as well as synthetic-based models, show also a high positive bias regarding Caucasian whites. While standard deviation and skewed error ratio on RFW indicate higher biases of synthetic models toward ethnicities, the results on BFW might indicate that a lower intra-class ethnicity consistency might be beneficial to reduce bias. With this, I conclude my talk and want to highlight that we observe similar bias in synthetic face recognition as in authentic models, which motivates the use and development of bias mitigation techniques also for synthetic models.